Okay, so welcome class. This is part 2 of our review. I think there was a question from the previous review sheet that I didn't get to finish on part 1 of my video, so I think I'll have to tack that on as a separate one. But you'll have all of these for video, don't worry. So let's see. As I said, this is probably the least popular question. Students just don't like the limiting reagent. Well, let's see what's not so bad. I would say part A and B are not difficult because what are we doing? We're given the masses of NH3 and O2, which are your reactants. And in order to find out what the limiting reagent is, I'm going to have to first find out how many moles of each one are being reacted, not necessarily used up. So I'm going to have to find out how many holy moles of NH3 that I have, and how many holy moles of O2 that I have. If you remember, that is mass divided by formula mass. That is mass divided by formula mass. Be careful, that's O2 is 32. Oh, and this is interesting. Both happen to be 2 moles. So I have 2 moles of NH3, and I have, of O2. Oh, I'm sorry, notice what I did. We even made it easier. That's A, and B, I've already done here. I'm finding out how many moles of each one that I have. We've set it up very nicely. Okay. So that's that's A, that's B. Part C, this is how we determine limiting reagent. Well, guys, remember, you take the moles of the reagent and you divide by the coefficient. So then we compare, and then we're going to choose, obviously, we want the lowest quotient. So we found that in both cases I have 2 moles of NH3, and I have 2 moles of O2. Notice the coefficient in front of NH3 is 4, so we get an answer of 0.5. And here, 5, 0.4. Yeah? Am I right about that? 2 divided by 5 is 0.4?
Yeah.
That makes sense, right? So that means ding, 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 ding. This must be the limiting reagent. Now be careful. It's still 2 moles of O2. We only use these values for the sake of comparison in this part of the question, merely to determine which one gets used up first. So that's the limiting reagent. Guys, we just found out that the limiting reagent is O2. Now, they have another question now. Having found out the number of moles of limiting reagent, we now can figure out how many moles of H2O I made. I have to base that on the number of moles of limiting. We said that I had 2 moles of O2 as limiting, and I want to figure out how many holy moles of H2O I produced. Well, notice I took the time to rewrite the formula because I need to get the ratio. There are 5 O2s for every 6 O2s. So I make a conversion factor. There are 6 H2Os for every 5 H2Os. I'm sorry, for every 5 O2s, silly Sigoki. Let's do the math. Bang, right? There it is. They're going to be amazed. 2.4 moles of H2O were produced. Okay. Guys, part E, if you notice, I wrote down the subtraction that we have to perform. I know that I had an original amount of NH3. That was actually 2 moles. That was up top. And I'm going to need to figure out how many holy moles of NH3 I used. And when I take that difference, well, that's easy. Then I can find out how many moles of NH3 are left. Shout out to Zoe. Question is, how do I figure out how many moles of NH3 I used? Remember again, if I want to figure out how much, like up here, how much H2O I made, or if I want to figure out how much NH3 I used, I have to base it on the number of moles of limiting that I actually used up. I used 2 moles of O2. I need a conversion factor, which is going to take me to the number of holy moles of NH3 that I used. Well, if I look at this, I notice that you had 4 NH3s for every 5 O2s. So that's 2 times 0.8. That should be 1.6. You'll tell me if I'm wrong, class. So now look, again, I had 2 moles of NH3 originally. I just found out I used, or I would use, 1.60 holy molies. What does that leave, class? Okay, Calais, what did you just figure out? What's the difference?
I'm out.
Calais has had a chance to calculate. Calais, shout.
0.4.
Thank you. So 0.40 moles are left. So, you had to get that in, didn't you? Okay. Pause. Okay, because we're hoping this works. Number 2, notice you're given moles. You are given volume of a gas. You're given temperature. You're given pressure. Well, guys, you have to use the ideal gas equation, which we like to call Pivnert. If you you're given this, but if you had to remember it, Pivnert would be the way to do it. Now, of course, you have to be careful. That is degrees Celsius. We need to change that to degrees Kelvin, and when we do that, we find out we are plugging in 546 to the temperature. Always be careful about that. You're told the universal gas constant, 0.821, that's given to you. And, a little mysteriously, that's the number of moles of gas. The volume we said was 2.00. And we're going to right now solve for pressure. Let's do it. Bang, about 269 atmospheres. Okay, let me pause for a moment. Bang. Okay, we're back. Notice here we're given the normal boiling point. We are given a solute that we are dissolving. We are given something called molality. And we have a special formula for this. The difference in the boiling point is always equal to something called I, which I'll say more about in a moment. The boiling point constant for this particular solvent, and little m is molality. So let me also write another formula up here. Now, as soon as we find out what the difference in the boiling point is between the pure solvent and the solution, we can then plug it into this little formula. We know that the boiling point of water, pure water, is 100. So when I solve for delta T, I will know exactly what the boiling point of the solution is. Now, let's solve for delta T. Well, we know that the molality of the solution is 6.0 molal. Kb, this is given to you. It's on a reference sheet, and you'll see that it is 0.52 with units. I'll leave the units off. Finally, we have to determine whether I is 1, 2, 3, 4. It could be theoretically 5, but it probably won't be. Notice in this case, I have Na, and I have a polyatomic ion. So that means I have 2. 2. Good, very good. I saw someone holding up their little cow horns. Little 2. Let's do the math. Bang. I just found out that the difference, the change is 6.2 degrees. So guys, look. We put this over here. So we find out that the new boiling point is 106.2 degrees Celsius. Ooh, don't put your fingers in that. You get your fingers burnt. Bang. Guys, number 4, this is the famous Hess's Law problem, meaning we take given delta H's, we maybe rearrange them. Ultimately, afterwards, we're going to add up the givens after they've been altered, and we can find out the delta H of a known reaction. Well, first I see, this is what I need to have. Starting with the carbons, notice I have carbons, but only one of them. So I'm going to have to multiply everything upstairs by 2. So when distributed, notice I have 2's everywhere, and I now have for this one 262.6. The next one I look at, don't look at water because I have water everywhere. You can get confused. Let water take care of itself. CH4, I need one CH4 on the product side, I have one CH4 on the reactant side. I got to switch the reaction around. Bang! When I reverse the reaction, notice what I have. Mathematically, reversal is like multiplying by -1, so I multiply this by -1. The last thing I notice is I have to have CO2 on the product side, just one of them, which I do, my friends. So that means we keep this one fine. Really, at this point, you could just then add these up, but let's see why. Let's see how everything cancels out. Guys, I dove into canceling. Notice that one of the H2Os here is cancels out the extra H2O, and we're left with the H2O we need. What else cancels out? Notice I have two CO gases. Now, there are no CO2 gases here. And fortunately, I have a CO2 gas and a CO2 gas. These two CO2 gases cancel those two CO2 gases. What else cancels out? Ooh, spicy. I have 3 H2 gases on the reactant and 2 + 3 H2O gases on the product. Those cancel out. I believe we're just left with everything that we need. 2 C2 solids. I have a CO2 gas on the product side. I have the two Wawas, and of course the lone CH4. Ding, ding, ding. So guys, we have the green light to add up. Bang! Notice here, guys, we just added up 15.3 kilojoules. Let's move on to the last question with methanol. Hey, guys, number 5, they are giving you an equilibrium expression. I'm sorry, they give you an equilibrium formula. We have to write an equilibrium expression. Guys, remember, this thing called this equilibrium constant is essentially a ratio of the concentration of products to the concentration of reactants. Now, of course, the products are here, and remember what we do. The equilibrium expression is CH3OH, that's that concentration of gas, and we would raise that to its exponent. Well, of course, that has no effect, because raise something to 1, it's just the same as it was. Then I have our two gaseous products. I have carbon monoxide, we raise to a 1, doesn't affect it, times H2 gas, here we go. I have 2 as a coefficient. I raise that concentration 2. Shall we plug in the values, class?
Yeah. Bang.
Bang. Guys, this is the equilibrium expression with the equilibrium concentrations substituted in. And of course, I think some of my eager students have already... What have you calculated, guys?
1.04 times 10.
What? You have to speak up.
You just repeated.
I'll do it.
Guys, I'm waiting for my
Pause
class to
it.
tell me.
Oh my god. I got 1.04
1.04.
times 10.
Yes.
-5.
Negative fun.
5.
-5. No units, guys. And that is advanced topics for this year.
Yay! That's wrong.
Oh, bang. Guys, we had a little bit of a
Trust me,
miscalculation.
I got it wrong.
It's actually 10.5. Oh, now that's the end of advanced topics. Yay!
Wait, you gotta circle the actual right one. In red. Yeah, cross out that one. Cross out one.
Okay, so there's no doubt about it. Yay! Shout out.